Okay, we are now looking at problem 8 of section 2.3. I do want to draw your attention to the fact that this is a word problem, and I know a lot of times we can get discouraged from word problems. You can't avoid word problems if you're going to go to the degree of calculus in math. So just kind of, accept that you're going to encounter word problems. You're going to encounter what they call application problems, and you just have to go through it. The best way that I approach word problems, first of all, is I just kind of skim. Okay, and so I say at a sand and gravel plant, sand is falling. What's the end result? What am I really looking for? And it says at what rate is the height of the pile changing when the pile is 2 feet high? So the height, when is it changing? That rate of change is going to be, assuming that the height is affected by time, I'm going to want that dH dt. Okay, now I'm going to go back through and read it with more depth. At a sand and gravel plant, sand is falling off a conveyor onto a conical pile at 16 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 2 feet high? Okay, so a visual, we have this, cone, the sand is falling, and, you can just imagine all this little sand here in this cone. We're looking for, let me make this cone a little bit larger so we can really work with it. In reality, it's probably not, wouldn't probably fall into a perfect cone pile, but for the sake of this problem, it is. Okay, so we have a conical pile and it's falling off the conveyor belt at a rate of 16 cubic feet per minute. So this pile is increasing, the volume of it is increasing at a rate of 16 cubic feet per minute. And so they don't tell us specifically that that's the volume, but the fact that they're using cubic units, that gives me some kind of idea. Okay, cubic is usually a measure for volume, and then also it's adding to the pile, so that's going to add to the volume. And it's that rate is that key word there too. So we have the rate of it's changing, it's increasing at 16 cubic feet per minute. The diameter of the base of the cone is approximately 3 times the altitude. So we do have the diameter, and I'll use D for that, is 3 times the altitude. Okay, so the diameter, we have our altitude. I'm going to say that's H, that's the same as the height. That's what they're talking about when they say the height of the pile, that's the same as the altitude. If you think of the pile as a cone, that H is going to be equivalent to the height of the pile. So we have that diameter is equal to 3 times H. And then we are also given that the height, because we're really looking at when is the, at what rate is the height of the pile changing when the pile is 2 feet high. So we have that the height is 2 feet. Okay, and they give us an equation, which is really helpful. And you can expect that on a test in most of these problems. I won't ask you, to know all these different kinds of geometric formulas, although there are some geometric formulas in the resources on Canvas under the modules page, but you shouldn't need that or be required to memorize them. But with this one, unfortunately, it doesn't give us a formula as exactly as we need it. It says that the volume is equal to 1/2 pi r squared times H. Now we certainly have H. We're given information about H, but we are not given information about R. And even if we had R, or that we aren't given anything about how R or the diameter is changing. So that's kind of problematic. But we do have that D equals 3 times H. So I really want to rewrite this formula so that it doesn't use diameter, but instead uses radius or height. Now, hopefully you know circles and know that the diameter is twice the radius. And so because the diameter is equal to 3 times the altitude or height, oops, how about I put that as an R? Then 3H equals 2R. We can isolate R and get R expressed in terms of 8 just by dividing both sides by 2. So then we have that the radius is equal to 3/2 H. So from there, I can say, okay, the volume is going to be 1/3 pi. R is going to be 3/2 H squared times H. And I like this because now we're just dealing with one variable. And when I start differentiating with respect to time, I don't have to worry about R's and D's in there because I don't have any given information about the diameter or about the radius. I probably could find that, but we don't have anything about how the radius is changing. And so just substituting it right here kind of saves us some time. So then I have V pi. I'm going to square this. This is going to give me 9/4 H squared times H. Or we have that V is equal 9 times 1/3. We have 3/4 pi H to the 3rd. Okay, so now I have volume in terms of just the altitude, which is great because that's what I'm given the most information about. So I'm going to go ahead and differentiate both sides with respect to time because both volume and height are functions of time. So I'll take d dt. And on the left, I'll have dv dt, which is unfortunately not what we're looking for. And then on the right, I'm just going to use the chain rule. So the derivative of the outer function, we're going to get 9/4 pi h to the 2nd, and then times dh dt. Okay, but remember, dh dt is what we want isolated. So I can take this equation, and just because I need more space, I'm going to erase our picture. This isn't a very great picture anyway. And I'm going to go to the left, which I know is out of order in the way that we read, and that just happens sometimes with space. Okay, so we have here dv dt. We're given that. So on the left, I have 16 cubic feet per minute. And that's going to equal 9/4 pi. H is going to be 16, or we're dealing with H being 2 feet. So we have 2 feet squared. And then we have that dh dt, which is what we want to isolate. That's what we want to find. Okay, so it's a little bit trickier in that what we want isn't on the left-hand side already isolated. Okay, so then I'm going to go ahead, and I apologize that this is kind of a little bit sloppy just due to space that I have. I'm going to divide both sides by the 9/4 pi and then this 4 feet squared. So really, you can think of that as a fraction. We're going to multiply by the reciprocal. So I will have 4 and then 9 times 4. This is going to give me 36 feet squared pi equals dh dt. Okay, let's go ahead and cancel some like terms that we have. So definitely 4 and 36 each have a common factor of 4. So I have 1 and 9. 9 and 16 unfortunately don't have any common factors, but feet cubed and feet squared do. And they have a common factor of feet squared. So I have 16 ninths pi feet per minute. For this one, I would approximate it because it just doesn't look nice to say 9. I mean, the denominator is not rational, you know, that 9 pi. So I would definitely encourage you to rationalize that denominator. Calculator that works. So we look at what is 16 divided by 9. 5. So I get 0.566 feet per minute for that rate of change.